Okay, so welcome everyone to the second of the Chandrasekhar lectures. So all of you were here yesterday. And Juan is today going to talk about a very interesting new development in string theory about the SYK model and its relationship to Ads2 gravity.
Okay, thank you. Can you hear me? Yeah. So these are some references. You can, I guess, look at them later. So I'll start with some orientation. So there are different models for holography. So we discussed yesterday the very strongly coupled theories that are dual to Einstein gravity. So here, this side is very hard, so we have to do computational strong coupling. And this side is relatively easy because you have to do simply computation in Einstein gravity. You could, on the other extreme, you could consider free boundary theories. And they are supposed to be dual to bulk theories with massless higher spin fields, so the theory of Vasiliev gravity. And that's a somewhat complicated theory where it's difficult to do explicit computations. Going away from free theories, you can have ON interacting theories, and they have some slight interactions, and they are sort of slightly massive higher spin fields. Now, one way to characterize the difference between the various theories is to look at the anomalous dimensions, or the dimensions of the fields with a spin bigger than 2. So the elementary fields in the bulk that have higher spin. So in a theory of gravity, the elementary fields have spin, of Einstein gravity, have spin up to 2. So spin 2 for the graviton, and all other fields have spin, elementary fields have spins less than 2. Of course, if the field is not elementary, you can have any spin, right? The hydrogen atom can have any spin. But here we're talking about the spins of the elementary fields and elementary bulk fields. And so in the free theories, they have 0. These are exactly conserved currents. In the ON theories, they go like 1/n. And here we're going to discuss an intermediate case, these SYK models, where these dimensions are of order 1. And so we have order 1 masses for those fields in the bulk theory. So that's more or less how they fit in the spectrum of solvable models. So they're somewhat in between the two cases. So let's just now review some examples of solvable large N models. And so a very simple example of a solvable model is one which contains only rainbow diagrams. And there are many models in this class. And again, I'm mentioning this for general framing the general discussion. So here you have some field, let's say in blue, and then you have some objects. So this could be like gluons that propagate, but they only attach to the fields in blue. They don't have any self-interactions. So an example of this is, let's say, 2D QCD, where if you choose axial gauge, then there are no interactions between the gauge fields, and we only have interactions between, here this would be a quark line, and this would be a gauge field line. A very similar story appears in large N Chern-Simons theories with fundamental matter in 2+1 dimensions. Again, by choosing axial gauge, you remove the self-interactions of the gauge field, and at large N, you only get planar diagrams that look like this. So there are no diagrams where these two lines cross. Okay. Now, if the diagrams have this structure, then you can sum them relatively easily. So think of the full propagator is the sum of various one-particle irreducible parts. So each green thing, you could call it the self-energy called sigma, or the one-particle, or the, yeah. And so, and then this piece itself, since it cannot be reduced, it has to have one of the red propagators, and then inside it could have the full set of propagators. So we get a closed system of equations where we say that the full propagator, so the first equation is really summing this geometric series in terms of the green thing, which is the self-energy, and then this self-energy is this propagator times the full Green's function or propagator for the other fields. So that's the nature of these equations. And let's discuss a very special case, which arises when the propagator is just a constant. And this is the same as what we get in the following model. So imagine you have n Majorana fermions, and you have a simple quadratic Hamiltonian of this kind with some random coefficients. So this is the model. And in this case, when you so you can think of J as an additional field, and then you will have a contraction between two J's. That is that propagator, which would be a constant. It's time independent because the J's are time independent. And so, so if you think about it that way, treating the random couplings as an extra field, this is not exactly the correct way to treat the random couplings, but for the approximation, it will be correct. And then you can, you get the solvable model with the structure of Feynman diagrams that we had before. Let me say a few more words about this special solvable model. You can, because it's quadratic, this model is actually integrable. You can diagonalize the J's, and you get a bunch of fermionic harmonic oscillators with a range of frequencies. And if J is a random matrix, then if you will have as a function of the frequency of those harmonic oscillators, so you will have some distribution of states, and the distribution is roughly like a semicircle distribution that comes from the random matrix that we had here in the beginning. Notice the random matrix here is the couplings, not the full Hamiltonian. Full Hamiltonian is a bigger matrix. Yes?
Rather than,
yeah, that's right.
But in large N, perhaps if
In
only
large
one.
N, especially for the SYK model that we'll discuss later, this is good enough. What I'm talking about now is the right way to treat this model. And so we diagonalize the J's, and then at low energies, we get this more or less constant distribution of frequencies. It looks a bit, that constant distribution looks a bit like a massless fermion on a big circle of size n. So if you had a fermion in a circle, and you ask, so you'll have a bunch of frequencies, right? And they're equally spaced. Here they are not equally spaced, but they have a constant distribution as a function of frequency. And so you get something like that. So you see that at low energies you have some emergence of some scale invariance. It's like the scale invariance of a fermion on a big circle. So this model is too simple, so it's not, well, you might think that this is somewhat similar, this could be a toy model for a near extremal black hole, which also has a scale invariance, as we'll see later. But this is too simple. There is no chaos, there is no black hole like behavior, and so on. Okay. Okay, so this I just mentioned just to contrast it with now the model that we are going to talk about. It's very similar to the one we saw before. The difference is that now we have a 4-fermion interaction as opposed to a fermion bilinear. So this model is now not solvable. So it's not directly solvable, diagonalizable, or it's not integrable completely. But it is still solvable in the Larsen limit using those planar diagrams that or special diagrams that we mentioned before. So here we'll have these couplings that are drawn from a Gaussian distribution. And to lead in order in the 1/n expansion, we can treat J as an additional field. And this will be correct up to a certain order in the 1/n expansion. And we will be, so J is a dimension-full coupling. So psi's are dimensionless, and J is a dimension-full coupling. And the theory is trivial at very high energies. There is some feedback. Yeah. So the theory is trivial at very high energies. And at low energies, it becomes strongly coupled. And we're going to be interested precisely in that strongly coupled region, where the times J are very large, or the inverse temperatures times J are very large. So these combinations are the effective couplings. And we're going to take them to be very large compared to 1, so that we are a strong coupling, but not so large that they become bigger than n. So in this regime, we can consider a special set of diagrams, and that's the regime we're going to study. So that regime corresponds to the following. So this system has a finite dimensional Hilbert space. And if you can diagonalize, in principle, the Hamiltonian, you could diagonalize it numerically, for example, and you'll get a bunch of energy levels. I mean, you have a large number of energy levels, an exponentially large number, because it's just a dimensional Hilbert space. And when we focus on this low energy region, we are focusing near the end of the spectrum, so we're focusing on those low energy states, but still keeping an exponentially large number of states. So we're not focusing on the very last state, right? So when we say low energies, we're not taking the super very low energy, exponentially small energies. We're just taking energies which are relatively low in this distribution. Notice that, there are random couplings in the Hamiltonian, but the full Hamiltonian is not a random matrix. It's not a random matrix in the 2 to the n times 2 to the n Hilbert space. Okay. So the number of couplings random couplings is proportional to n to the fourth, not to 2 to the n. So it has a little more structure than the generic random matrix. Okay. What? Well, I'm just trying to explain the difference between this type of Hamiltonian and a random matrix Hamiltonian, right? So this Hamiltonian has a special structure. It's not the number of parameters is smaller than the number of parameters in a generic random matrix. So generic random matrix would be a sum of terms like this with 2 fermions, 4 fermions, 6 fermions, etc., all the way up to, let's say, n fermions, or maybe n over 2 fermions. So that would be the generic random matrix. This is something more restricted. Okay, so now, so before we had this kind of diagrams, and so now we have a very similar structure where we have the propagator of the J's, which again would be constant, and then the propagators of the fermion fields, and it can be solved exactly in the same way as before. So we have the self-energy, and now the only difference is that the self-energy is proportional to the propagator to the cubed power, and that is related to the fact that here in the expression for the self-energy there are 3 lines. But that's the only difference relative to the previous class of solvable models. So it's the fact that there was a 3 here as opposed to a 1. And then you can generalize the model by taking q fermions as opposed to 4 fermions, and that is useful sometimes. And then you just get the q minus 1 here. So here q equal to 2 was the case we had before. That's a very trivial model, not so interesting. Q equal to 4 was the original SYK model. And when you take q very large, you can actually solve these equations analytically. In general, you can only solve the equations numerically. So this one equation is simple in Fourier space. The other equation is simple in time and position space, if you wish, or time. And then you somehow go between one and the other, and by some iteration, you can solve the equations numerically. Now, there is a situation where you can do a little better. You can make write down an analytic solution, which is when you go to very low energy. So you go to very low energy. So the previous equations are valid for any energies at a large n. So here you can consider any energy and always large n. They are true to leading order in the 1 over n expansion. But now, if we go to low energies, what happens is that we can simplify the equations by dropping one of the terms, just the standard UV free propagator. And in this case, then you can make a scaling ansatz for the solution. And then you put in the solution here back into these equations. You can, by simply Fourier transforming this and checking, and then, putting them back into this equation, you can check that this is a solution only if delta is 1 over q or 1 over 4 in this particular case. So you can determine these anomalous dimensions of the field very simply by putting them back into the equation. This should be compared to, for example, in n equal to 4 superior mills, it's very difficult to determine the anomalous dimensions of operators at strong coupling. Here, you just simply solve these 2 equations. Now, in fact, when you drop this, the equations have a certain symmetry. And the symmetry is that if you have a G which is a solution, and you're given an arbitrary function of time, then you can generate another solution by doing reparametrization. So you take a solution like this, and then you define a new function of 2 times, which is given in terms of the function of 1 time that you are given, by this formula. And this formula looks like a reparametrization of the original correlator. And in this way, you generate a new solution. So as an example, we can consider this particular reparametrization that maps sort of an infinite line to a line of tau here is a periodic variable of period beta. And then, so that's like the map between an infinite line and a circle. And when you do that map, then you get this solution, which is the solution at finite temperature. So if you get this, if you write down the scaling ansatz, that would be like the very zero temperature ansatz, then you can go to the finite temperature solution by this input transformation. So that's an example of the usefulness of this relationship. And okay, so now let me just say what the general form of this propagator is. So this is in Euclidean time. So when I'm now not going to go to log inertias, I'm going to describe the solution for any value of the inertias. So let's consider the case of very high temperature, so beta j equal to 0. Then this propagator is just a constant. So in this case, we can neglect the Hamiltonian is not important. And when you put two fermions, you can put them at any distance, and you'll get always the same answer. Okay? So it's just a constant. As the effects of the interaction become bigger, then the propagator, well, when they are at coinciding points, you get psi square, and by the commutation relations, that should be 1/2. So everything should match here to 1/2. And then in the middle, the fermion is transforming into other fermions, so the correlation function becomes a little smaller. And when beta j is much bigger than 1, then you get some function that roughly looks like this. And the sine function that we saw before is one where we approximate this by something, well, which is singular at tau equal to 0. At a very small tau, it will go over to something that goes to 1/2. So in most of the range, so for times which are so here we are at very large beta for times j bigger than 1. So this little region where it differs is when times j is less than 1. So when times j is bigger than 1, then we go over to this type of solution. Okay, so that's the mechanics of these solutions. Now, one nice thing about this model is that you can integrate out the fermions and obtain an effective action for these Green's functions. More precisely, you can start from the original path integral of the fermions and rewrite it as a path integral over fields sigma and g, which are functions of 2 times. And the classical solutions of this action will be the actual correlators. So let me just outline very quickly how that derivation is done. So you start from, this was the Hamiltonian that we had. We write it in the Lagrangian formalism. So this term gives you the commutation relations for the psi's. And then this represents these are the Gaussian, well, this is the Gaussian distribution for the fields J. So now we integrate over J and psi, right? First we integrate over J, and when we integrate over J, so J appears quadratically, we just complete the square, and we get the psi to the 4th interaction. This is very similar to the steps we do in the ON model, for example. The only difference is that in the ON model, this field is a function of time. And so, but here, because it's constant and independent of time, we get here a double time integral, and we get psi at 2 different times. Okay, so that's what we got so far. And then to simplify this a little more, we can introduce a variable g, which is essentially, so we insert a 1 in the partition, in this fold partition function, which we write as the integral dg of g minus psi squared. So that's defining g as psi squared. And then we write the delta function as an integral over sigma of sigma times the thing that we want to, the argument of the delta function. So we insert this in the partition function. And after we insert this, what we find is that we can, because of this delta function, we can replace this by a g to the 4th term. And then the fermions, after you do that, then the fermions appear purely quadratically, just in this term and that term over there. And then the integrating over the fermions, you get this determinant or Pfaffian. Just Pfaffian with Majorana fermions. And then similarly here, you get this term that we already had here. So the nice thing that happened is that there is an overall n in the action. There is n appears now as a parameter. It's not the number of fields, but it's an overall parameter. And for large n, it plays the role of 1 over h bar, so the system becomes classical. And the diagrams we were summing before, and the equations we had before can be viewed as the classical equations of motion of this action. Okay? So if you take the classical equations of motion of this action, you recover the solution, the equations we had before. Okay, so this action is correct to leading orders where we ignore the correct treatment of this order, and that's valid up to order 1 over q minus, I forgot the 1 over here, up to this order in the expansion. And similar actions, you can obtain similar actions for ON models, so you might have seen those already. So low energy, we had this simple solution. Now, you are used to the fact that in other dimensions and in other situations, if you have scaling invariance, you typically also have conformal invariance, right? Now, in one dimension, conformal invariance would be the full reparametrization symmetry. So because the only component of the metric is just the diagonal, so rescaling the metric. Any reparametrization just preserves the metric after rescaling. And in fact, this is an invariance of this action, of the low energy action. So if we take this action and we neglect this dt, you can argue that this is a reparametric symmetry of this action. And so if G is a solution and we are given an arbitrary function f of t, then we can generate another solution in this way. Okay, that's what we saw before, and that's a symmetry of this action. And you can view this as an emergent reparametrization symmetry that we have at low energies. So we had this story, and now one thing that makes this situation different than the situation in other dimensions is that if we have this symmetry, then if we started with one solution and we act with this symmetry, we generate a new solution. Okay, a new configuration that has exactly the same value for the action. Right? And so there is an infinite number of configurations that have the same value of the action, parameterized by the choice of this function f. Okay? That's what happens at low energies. So they have the same value of the action in the strict infrared limit. So by the strict infrared limit, what I mean is neglecting this dt. Okay? So in that limit, if you just take the action in that limit, all these have exactly the same action. So they look like a Goston boson. So we have this symmetry, but it's realized as in the it's spontaneously broken by the choice of one of these solutions, and we have this infinite number of Goston bosons. And this would give a divergence if we did the path integral over f. So doing the path integral over f, we get the divergence. And the solution but that would be wrong because the original problem had a finite dimensional Hilbert space, right? Everything was finite. There is no way we can get a divergence. Okay? So if we're getting a divergence, it's because we're doing something wrong. And the wrong thing we are doing is to have gone to this strict infrared limit. We should remember that this symmetry is also slightly broken by that, essentially by these UV terms. And that implies that we'll get some nearly zero modes. So there will be a small action for this f. And now the deviations from the conformal solution were expected to happen at short distances. Recall the plot we had for the propagator. It was differing from the exact propagator, was differing from the low energy propagator at when the two times were equal or close to equal. And so we expect, that implies that we expect this would be a good solution, except when the two times are equal. And so that implies essentially that the effective action that we expect for f should be a local action. So it should be an action that involves a single integral over some f or perhaps derivatives of f. Okay. Now another point that is important to derive the action is to notice that, we said that this function spontaneously breaks the reparametrization symmetry, but that was not exactly true. So there are some transformations that leave the action invariant, that leave this function invariant, or that don't do anything. So if we take some f like this, and then we change f by an SL2R transformation, then the actual functions we get are going to be exactly the same. And so this is just simply a redundancy in the parametrization. So whatever action we write down, it better be that it's invariant under SL2R, this SL2R, simply because this SL2R is not changing the actual functions. So two functions that differ by this SL2R should have exactly identical action. So the simplest action we can write down, which has these properties and the smallest number of derivatives, is the so-called Schwarzian action. So it's this combination of derivatives. It has the property that, well, it's local, it's just a single integral over time, and SL2R invariant. There are other SL2R invariant things you could write down, which are, let's say, for example, powers of this Schwarzian. Those are higher derivatives. Those are further contributions. But now this is an action which has a net number of 2 derivatives, so that implies that the coefficient here should go like 1 over j. Okay, so that's just dimensional analysis. And indeed, you see that when j is very large, so we are very low energies, the coefficient becomes very small, right? But we cannot set it identically to 0, because then we would get 0 action for this and we'll get the divergence. It's proportional to n because the whole original action we started discussing in terms of g was also proportional to n. And there is a coefficient that we can determine by these arguments. You have to calculate it numerically by matching the short distance solution to the long distance solution and so on. Yes. Well, all of this was for large n, but low energies. So the strict, very extremely low energy limits has a problem, and then it's fixed by remembering j is finite, not infinite.
Right, but this infinity could be cured also by going to finite n instead of the...
We're discussing, so far we've been discussing the theory at large n, right, to lead in order in the 1 over n expansion. And in fact, to lead in order in the 1 over n expansion, you have this issue. It is true that you could take some limit of very large n and j and go to some regime where quantum fluctuations of the Schwarzian would be important. Yeah. But I think in the analysis of the theory, it's always important. This is an important effect, and you will always be there.
Right.
Of course, if you're at finite n and you go to extremely low energies, there is one state that is the ground state, and that's it, right? So everything becomes trivial. But there you need to go to exponentially small energies. That's the picture we were showing of the spectrum.
I see.
Okay, so here, this SL2 symmetry is a redundancy in the description of the various configurations. So we should think of it as a gauge symmetry of this theory. So we are going to quotient everything we do by this SL2R symmetry. Okay, so at low energies, we are at low energies, we had the original functional integral, and for many long distance and low action configurations, we can replace the functional integral by an integral over this mode f, right? And then fluctuations in g and sigma that are somehow orthogonal to this direction of changing this reparametrization. So that's what we can do. And when we look at some calculation, for example, the calculation of the 4-point function. Yeah, let me go back here. So this piece will be an action that will be purely conformal invariant. So this piece will be independent of j. J is a dimensionful coupling. So this whole stuff will be independent of j, but this thing will depend on j. And at low energies, the effects of this that have to do with the functional integral over these variables will be amplified relative to the ones related to the functional integral over the rest of the variables. But you should think of the theory as containing these two parts. So one is the conformal invariant sector. That will be, when we go back to ADS2, that will be related to fields propagating on ADS2. And then this other sector that, as we will see, has to do with the graviton in Ads2. Yeah. Yes.
Part of it, which is the SF.
Yes.
So then you can write down explicitly what the S conformal is. The remaining part is you can just separate it out into the modes and okay.
Yeah. I don't remember where I was going to discuss this. So if you, so for example, we can calculate the 4-point function. So let me show you how more or less this works for the 4-point function. So a 4-point function can be written as an path integral over g and sigma of g of tau 1, tau 2. That's the first two, and then g of the second. Now here we're integrating over these g's. So there's a piece that will be evaluating the classical solution that will give you the disconnected part of the correlator. And then a piece that comes from the Gaussian piece here in the action. Okay. And the Gaussian piece, there is a part that is independent of J that comes from the sigma prime and G prime, and then a part that it comes from F, and that will have an extra factor of J. So let's discuss first the part coming from the Schwarzian. So there, what we do is we take these G's, we don't integrate over all possible G's, but only the G's that are reparametrization of the original solution. So this GF is the expression we saw before, right? So it depends on F. And then we do that functional integral over F, and we'll get some function. So to lead in order, we'll, in 1 over n, we get this, some particular function that has this enhancement factor. So for large beta J, is bigger than you would have expected. Okay, so that's this leading part. And this contain, I won't discuss it in detail, but you can, this piece in particular contains the leading contribution to the out-of-time order correlator, so the piece that grows exponentially with time and characterizes it's related to the Lyapunov exponent of the system and so on. It just purely comes from this 4-point function. I'm not writing the expression explicitly, but it's not too complicated. You can calculate it fairly explicitly and write down an analytic expression and continue to Lorentzian signature in various ways so as to compute this, the correlator with various time orderings. So in particular, you get this a correlator which goes like this in Lorentzian time. So this is now Lorentzian time, and has the maximal chaos exponent, saturating the chaos bound, and again, this prefactor that we expect from these more general grounds. And the full 4-point function includes, well, this is the piece we've been discussing, and then it includes a piece that comes from this conformal invariant part that is completely conformal invariant. So this is not a function of the 4 times independently, but it's a function of only the cross ratio. It's a non-trivial function of the cross ratio. And you can, again, say explicitly what it is. I won't discuss exactly what it is, but it contains, if you do an OP expansion, it contains contributions from fields which you can think of them as bilinears of these fermions with some dimensions, and these anomalous dimensions are the ones that I was previously saying they were of order 1. Yeah, so it's a little more messy to get this one. So these are some pieces which, yeah, essentially subleading pieces from the Schwarzian and some. So when you do the splitting between the two, the Schwarzian and the rest, there is also some mixing between the two things. And, but you can calculate it and get some answer for it. But in order to write down the full 4-point function, you need to discuss it a little bit because it's of the same order as this one. Yeah. Unless you act with certain differential operators to somehow get rid of this and I don't know. I don't think it's just simply a Jacobian. But yeah, it has to do with the fact that the full Hamiltonian has corrections that mix the well, these modes, the simple modes that are related to F, and the rest of the modes. The full Hamiltonian to order 1 over J is mixes these two. Now here, this is a random comment. It's just a comment. So people in the past, they've discussed that they discuss simple actions like x squared plus g over x squared. This is a simple quantum mechanical action that has an SL2R symmetry. And for this reason, people thought they might be related to extrema black holes. But it's really, here the SL2R symmetry is realized in a different way. So in particular, in this case, we don't have an SL2R invariant states, and we have an exact SL2R symmetry acting on the dynamical variables. We don't have the reparametrization symmetry. And so we have really a different pattern of realizations of symmetries. And we'll see later that the pattern of realizations of symmetries in ADS2 matches the one we had in the SYK model. So the SYK model is a better, more faithful representation of the better model for ADS2. Now this action is fine for describing brains that are moving in ADS2, but they don't seem to capture the gravitational features of ADS2 properly.
These conformal quantum mechanics, their gravity dual would be something more exotic?
Yeah, probably. I don't know exactly what it would be. I mean, here we have the exact SL2R symmetry, and in the SYK model, this action for the reparametrizations breaks the SL2R symmetry. It's important that the system is not SL2R invariant, while here it would be. Yeah, in this case, typically these quantum mechanics have a non-compact target space, and yeah. So I don't know. That's a good question. Yeah.
It won't be ADS2, right? This system.
For which system?
This model.
Well, so here what people have discussed is you can add an x squared term, and then there will be a ground state, and yeah, it will be a SL2R invariant, and so people have proposed that it was equal to ADS2. I think, as we will see later, when ADS2 gravity is important, that we are not have the SL2R symmetry is not exact. Okay, so okay. Now, there are a few questions about this that I think have not been understood. The question is how we think about this approximate symmetry and so on in a Hilbert space context. I mean, there are natural questions, which is there a Virasoro algebra? Everyone who's seen this Schwarzian always would like to find this Virasoro algebra and how it's realized in the Hilbert space. Is there any central charge that can be computed? These are all natural questions, and I don't know the answer to these questions. But they're the first questions that you ask. I mean, if you come from string theory, that you would ask, but maybe they're bad questions. Yeah.
I mean, if you're doing disorder average, then it's not clear that there's a sensible Hilbert space, right?
Yeah, so this is the description of the theory at leading order, but let's not do disorder average. Let's just consider a specific realization of the disorder. Let's do it exactly. But and as we'll mention, there are also the tensor models which share all these features. Now, let me just, for completeness, say a few things about the reparametrizations in CFT2. So actually, in two-dimensional CFTs, we also have holomorphic and anti-holomorphic reparametrizations. And they're also spontaneously broken by, you can view them as spontaneously broken by the vacuum down to SL2R squared in this case. And we also have Goldstone bosons. And in this case, it's different. So there's a non-zero action that you can write down for these Goldstone bosons. Could be in some approximations the Liouville action. But the particles created by the action of the symmetries are the modes created by the action of the stress tensor. Right? So we do have all these Goldstone bosons. They have an action which is exactly conformal invariant. So some aspects are similar to the SYK and some aspects are different. Right? So the first point is similar. The difference is that now we can have a non-zero action consistent with this conformal symmetry. So that's what makes the two-dimensional case different from the one-dimensional case. The symmetry in this case is not explicitly broken, so the Schwarzian action explicitly breaks the SL2R symmetry, the physical SL2R symmetry, and well, also here the symmetry algebra is deformed by the central charge term. So, yes.
So in ADS2, of course, the SL2R is broken. But the action vanishes for F being an SL2R transform. So it's
this is a confusing thing that I haven't explained properly. So let me explain it properly. This action has an SL2R symmetry of transformations of F. That's a gauge symmetry, and it's an unphysical symmetry. It's not the symmetry of anything. Okay, it's just a redundancy in the description. But you can also ask about SL2R transformations of the time t. Okay, in particular, for example, you can even rescale t. So this action is not invariant under rescalings of t, because there is one integral over t here, and there are two time derivatives, two net time derivatives. So it's not invariant. So this action is breaking the physical SL2R symmetry of time transformations in time. Sure, yeah. I mean, it is possible also to describe these Goldstone bosons without talking about this extra SL2R symmetries, a more physical, more reduced description. But we might describe it that way later. But yeah, that's a point that sometimes is confusing. And okay, so that's what we already seen. Okay, so one comment is that disorder is not fundamental to this story. We can have a model with interactions between, we can have a model which has fermions with 3 indices, and a 4-fermion interaction where the indices are contracted according to some particular pattern. And if you do this, then the large N equations coincide with the previous equations that we've already seen. And at sub-leading orders, it will be different than what we're discussing, but the leading order answers will be the same. So everything that I said so far would be identical for this model. So the conclusions is that the SYK model is a simple solvable model in the large N limit. So in the sense that the leading order in the large N expansion is solvable, and is strongly interacting and maximally chaotic. So that's a nice feature that it has, that despite normally when you have something solvable, it's too trivial and it's not chaotic. But here it is both solvable and chaotic. So it's in a nice region somehow. It has this interesting nearly conformal symmetry at relatively low energies, and so on. So those are all features of the SYK model. So now we go to discussing near extremal black holes. So we consider charged black holes, for example, and then if the mass is close to the charge, then at low energies near the horizon, we find an ADS2 region. And first, so this would make you think that perhaps we can take this whole limit to restrict to the ADS2 region, and then find perhaps a dual quantum mechanics system that describes those near extremal black holes. It will be some kind of conformal quantum mechanics system. Now, there is a no-go theorem that this cannot be done, and it's based on the following observation. So if you have a conformal invariant system, then the density of states can only be like 1 over E or delta of E. These are the only conformal invariant densities of states. And the density of states we have to reproduce the finite entropy of the black hole, right? So if we had this, we get a divergence from integrating at very low energies, which is precisely the region where this is supposed to be valid. So this is wrong. And this one might reproduce the extremal entropy, but it would reproduce no dynamics because we have only states at 0 energy. Now there's been a lot of discussion of taking ADS2 and computing partition functions of ADS2 gravity to get the extremal entropy, and that's a beautiful story, and it works very nicely. But if we want to consider dynamics of fields moving in ADS2 and so on, we need something else. It cannot be done within some conformal quantum mechanics theory. So also, if we take the simplest two-dimensional action, which would be like the Einstein-like action, the Einstein term itself is topological, so there would be no contribution to, no dependence on the geometry and no dynamics. And this story is fine for extremal entropy, but it's not fine if we want to describe any dynamics. So what you should do is you should keep the leading effects that perturb away from ADS2. So the leading effects that will break this conformal symmetry. And that consists in taking an action which, well, this was the topological term we had before, and this gives the extremal entropy. And then we add this other term in the action, r plus 2 times phi. And this, if you are coming from higher dimensions, for example, from 4 dimensions to 2 dimensions, phi plus phi naught would be the total area of the sphere. So phi naught would be the extremal area, and phi would be the deviation from the extremal area. Okay. And you would get an effective action like this, so the area is multiplying the 2-dimensional curvature. Okay, so this is a very simple theory. So if you vary with respect to phi, it imposes that the equations of motion imply that the metric is exactly ADS2. Then the equations of motion for the metric almost completely fixed phi completely. So there are no propagating fields in this story. In fact, they fixed the value, so the phi is almost completely fixed, and you can, by choosing the origin appropriately, you can write the ADS2 metric, and phi has this form. So phi depends explicitly on the radial direction, and is not invariant under SL2 transformations of the metric. So that's the statement that the solutions of this action break the SL2R symmetry. And okay, so now, the idea here is that phi sort of grows towards the boundary of ADS2, and at some point you will cut this off and match this to some higher dimensional space and so on. And you will cut this off at some value, when phi gets to some specific value. So at the boundary, we want to fix the value of phi. So boundary conditions will fix the value of phi, which is basically the point where this description will match on to, let's say, either 4-dimensional description or some other description. And so we are going to put some boundary at some large size in this ADS2 space, where we fix the proper length of the boundary, and then we also fix the value of this so-called dilaton field, or this value of phi at the boundary. Now, if we only consider metric configurations that fix only the metric, there is actually an infinite number of configurations which correspond to all the curves that we can write in ADS2 with that fixed metric, with that fixed length, fixed proper length. Okay. Okay. And this infinite number of solutions is related to the fact that ADS2 has a group of asymptotic symmetries, which is, again, these reparametrizations, the same group of symmetries we had in the SYK model, and they transform one of these configurations into another configuration. Notice that 2 configurations where this curve is different are actually different geometries. So one could be, for example, a circle, right? And the other one could be this shape. Both are some cutout of, so the actual geometry is the interior inside this curve, and this interior region is different. It's like when you have some dough and you cut a little bit cookie out of this dough, it's a different one in each case. So all of these should be viewed as different geometries, and if the action was only the topological part of the action, so ignoring the term with the phi, so the first action we wrote, they will all have exactly the same action. Okay? That's the feature that we saw before in the strict infrared limit in the SYK model. Once we impose the equations of motion for the dilaton inside and we fix the value of the dilaton, we select one particular solution, which happens to be sort of a nice round circular solution. And so in fact, you can make the connection very explicit between the two things. So you can start with the full action. So the action we originally wrote, and before I was dropping this boundary term, but in order to have a well-defined action, you need to put these boundary terms. This is sort of a Gibbons-Hawking boundary term. That arises because here there are second derivatives of the metric, and to have a well-defined variational problem, you need to add this boundary term. So K is the extrinsic curvature of that line. And so then, and phi, this should be a, well, here I put the function of u, but it's a constant. This is the constant value of the dilaton at infinity. And so this is a fixed function, let's say it's constant. And then when you expand, so when you imposing the integrating out phi, that sets a delta function that sets this to 0, so that we drop this, this part of the action, and we only get this extrinsic curvature term. And when you expand that extrinsic curvature term for curves that are very close to the boundary, you get a piece that is just divergent, that is proportional to the length of the boundary, and then another piece which is just the Schwarzian action that we were discussing before, where t is the coordinate along the time coordinate. In some, let's say, this particular case is in Poincare coordinates, and u is the proper length along that curve. Yes, it's also multiplied by phi and the total length. Yeah, this has some typos. Okay, so here t is the usual ADS2 time coordinate, so the Poincare time, let's say, and u is the proper length along the boundary and should be viewed as the quantum mechanical time coordinate of the quantum mechanical system, the actual time of that quantum mechanical system. And t is some kind of infrared time, effective time that the fields in the interior feel. Okay, so in conclusion, so nearly ADS2 gravity is very simple. So fields, here we only describe the gravitational sector, but we can add some matter. And the theory is really simple if the matter does not couple to the dilaton, which is a good approximation for cases where you can come from higher dimensions. And so fields propagate on a rigid ADS2 space, and the gravitational effects are related to the position of the boundary in that rigid space. So that's where, and you can think of that as being described by a boundary graviton. So similar to, let's say, three-dimensional gravity, where you don't have propagating fields, but you have some field that lives on the boundaries. In this case, the boundary has only the time direction, and so you have simply a quantum mechanical degree of freedom living at the boundary. And you can describe it in various ways. One way is with the Schwarzian action. And this has the same symmetry of pattern of symmetry breaking, and even the same action. The action is determined by the pattern of symmetry breaking as the SYK model. So let me summarize in this slide the relationship between the two things. Is this time correct, or? Well, 2 minutes. Okay. So so let me try to explain a little better the conceptual relationship between the two things, between the SYK model and gravity. Okay. In particular, I'm not saying that the two are equal. I'm going to make a more restricted statement. So we have the SYK model, and let's say we can have near extremal black holes. We can go to low energies, and here, going to low energies, we go to this nearly ADS2 gravity. Okay? And at low energies, the model sort of has a conformal invariant part, right? And this part that has to do with the dynamics of these reparametrizations. In this case, we have a quantum field theory in ADS2, so we have fields that propagate in ADS2. And then we have the boundary graviton, this boundary dynamics. These two are the same. So they're the same in the two models, and they are determined by the same symmetries. Okay? Now, in general, if you take some generic ADS2 setup, these two things are going to be different. Like the masses of these fields will not match, in general, the dimensions of any SYK model. And there might be, you might question whether there is a particular ADS2 gravity and some particular field content here, which matches all the physics of SYK. We haven't found that yet, and it's not known what it is. And it's believed that it won't be a local field theory, that it might be something more like a string theory, perhaps, or some other weird theory. And we don't, there are some proposals, but I think there's nothing that reproduces all the facts. So, okay, so now this part that is the same, determines lots of the physics of this model. So it determines many aspects. In particular, the simplest one is it determines the lower temperature entropy, near extremal entropy, that it should be linear in the temperature. And that's a feature of all near extremal black holes. The Kerr black hole, all black holes have this feature. And also it determines the chaos exponent. And also determines lots of things that have to do with wormholes and whether wormholes are traversable or not, and so on, that I haven't discussed yet. So there are many things that you can get just from the matching of these two things. And there are many aspects that will be the same in the two theories. Okay, so yeah, this is the same running over the same thing. So I go on, okay.
So the mode F in the SYK model, the Schwarzian in the bulk was a Schwarzian of this T with U, right?
Yes.
So the T is playing the role of I mean, it's not a field in the bulk, is it? Or how do I mean, it's this boundary graviton.
Yeah. So the idea is that let's say you have some metric, right, in the bulk, and then we are describing the motion of the boundary in this metric, right? So for that we would need to give what T of U is and what Z of U is, right? U is the proper time, right? So this T of U is a field that, like when you have a motion of a particle, right? The position of the particle in the ambient space is that field. That does clarify that? And then Z is determined in terms of T by demanding that the proper time is U. So I can do a little more explicitly. So we're saying that the proper time should be du up to some scale factor. This has to do with the limit we're taking. And so here, this is the same as saying that this is T prime. Let's say T prime over C, right? Here I have neglected the piece that goes like C here, because from this equation we're going to find that C is of order epsilon times T prime. Okay. So, and then a posteriori, then we check that it was correct to neglect this fact for small epsilon. So when you have this trajectory then close to the boundary, you can think of the position of, you can describe the motion just purely in terms of this function T of U. And then C is determined by the condition that U is proper time. Are there any other questions? Well, this is the picture of entangled states, and I think you've probably already seen this picture, so I won't dwell on it. Let me say a few more words about, well, basically continuation of this, what we were just discussing. When we think about the Lorentzian theory, we can think of full Lorentzian ADS2, and then we have the matter fields that propagate in ADS2, and we also have the position of the boundaries. And again, the position of the boundaries are, they describe the motion of some particles in that ADS2. So the whole, each of these systems, the right boundary, the left boundary, the matter and the left boundary, they all have an SL2R symmetry. Okay? That SL2R symmetry corresponds to translating the whole, I mean, if we act with a global SL2R symmetry, we translate this whole figure, right? But that we should view as a gauge symmetry. So if we, let's say we can have the Hilbert space of this particle, and so on, and the full Hilbert space is the product of all these three Hilbert spaces, but we should quotient by an overall SL2R, because the physics should not depend on the fact that we sort of shift the whole picture up or down. So shifting the whole picture up or down doesn't do anything. It's a bit like the Mach principle. So is that what's important is the relative position, let's say, of this boundary relative to this, or of the matter relative to the boundary. But the overall position of the matter and the boundary, you can change it and nothing happens. So Now, you can, well, I think I might. So I'm going to discuss just how to think about, with this picture of the motion of bulk particles and the motion of the boundary. The gravitational dynamics on gravitational back reaction is exceedingly simple. It's very, very simple to describe. For example, you know that if you have a black hole and you send some matter into the black hole, in some sense the horizon moves a little bit, and in the sense that some region that before was visible, now it will not be visible because you send some matter, right? And so now we're going to see how to see the same effect using this description of the motion of the boundary and so on. So here, imagine you have some initial black hole and corresponds to the motion of the boundary here along the red line and the dotted red line. And this is the original horizon. Then imagine you send some matter here into the interior. Okay. Then this, so locally here, we have to preserve this SL2R symmetry we said was a gauge symmetry. And locally it acts really like momentum conservation in 2 dimensions. And so if you are sending something to the left, then this boundary thing will move to the right. And it will therefore hit the boundary of ADS2 earlier than the other one. Now, when this trajectories hit the boundary here, there is actually an infinite proper time to the boundary. So really, this is describing the whole history up to infinite times here on the boundary. And so then there is a new horizon, which is now the blue dotted line. And so there is this region. There is some region here, which you could see before, and now you cannot see after you send in this particle. So that describes the gravitational back reaction is described in this simple way. Now, this, yes? Yeah.
If you have a... Okay, let's shoot. Do you have to send in only, are you considering only null things?
No, you can send whatever.
So,
yeah.
so if you send a time-like thing and you send it initially outward, it would anyway fall back in by the ADS to sort of geodesic, but then your trajectory would be different.
Well, you always send something to the left. What's important for the argument I was making is that you send something to the left and then the boundary is kicked to the right.
Okay, but what would happen if you send it the other way? It would still fall in.
No, you cannot send it to the right. I mean, here the idea is that only the left exists here. The right doesn't exist.
Okay.
So you can only send it to the left.
I see.
Yeah.
Okay.
Yeah. Yeah. Here we're sending positive energy things, which normal physical things have positive energy. When we were discussing wormhole traversability and so on, we were sending negative energy that can do the opposite.
Do that.
And that's why you can see more inside the black hole and so on. I mean, but negative energy things are things you have to be careful about how you are sending them because they're in general not allowed. One point I was going to make here, let's see. These 2 trajectories look that they are very close to each other, but really in the ADS metric, they differ exponentially by a growing, they differ by an amount that grows exponentially with time. I mean, this motion in ADS2 is roughly like motion in hyperbolic space, where you take two trajectories that are close by and then they deviate. And that deviation between the 2 trajectories is related to the chaos growth. And the growth with time is precisely this exponent. Now, to actually see this deviation, you need to do this more sophisticated out-of-time order correlator, because we said that we cannot really ask, well, if the absolute position of the trajectory doesn't have a meaning, only relative positions. And the out-of-time order correlator allows you to somehow measure that difference. But one important point is that this quantum chaos that had to do with the growth of commutators and so on is realized here geometrically as the motion of this, is related to the motion of these trajectories. So in some sense, on the boundary theory, so you can think of, well, you have chaos and it looks something complicated and so on, but it's described by a very simple classical degree of freedom. It's completely contained in the map that you have between the infrared variables and the UV variables. And that map changes, and that's responsible for chaos. So chaos in the bulk description is just a classical property and the classical motion of a particle. Yeah.
Exponent in the bulk.
Yes, that's right. But one little thing is that you really need to measure it with respect to the proper time. Yes. No, it doesn't tell you that that is why it should be the maximal bound. I mean, it just gives you one value. I mean, in fact, it's difficult to see in this picture how you would get corrections to this value. So I don't know how to modify this picture so as to get the corrections as you expect in, when you go exact ADS2 limit from this very low energy limit, we expect to have corrections. So for example, in the SYK model, as you go to higher temperatures, you expect the Lyapunov exponent to become smaller than the temperature. And this should be some modification of this geometry and so on, and I'm not sure how it happens. I mean, it's also been remarked by Jensen that this is similar to hydrodynamics. So this action for F is a bit like a hydrodynamic action for the conservation of energy, especially if you look at some of the solutions for the action. So, okay, so then I had a bunch of other things, but I think I'm going to skip them and end here. Okay, thank you.
So yesterday you mentioned that how we calculate this maximal bound on the chaos, when it has stringy correction, it can be a little lower, but cannot exceed that value.
Exactly. Yeah.
So in this case, we exactly calculated to have a maximal chaos bound. It's like 2 pi by beta. So does that tell us about what sort of, means if we do have a
yes.
string?
Yeah. So you might have, based on what I said before, what I said yesterday, you might conjecture that the systems that have maximal chaos have an Einstein gravity dual, and string corrections are small. But that's actually not true. So that conjecture is one might have had, and in fact we had, it was incorrect. So when you have a near extremal black hole, or these ADS2 regions, even if the bulk is stringy, the corrections are small. So in the limit of this nearly ADS2 limit, these stringy corrections actually disappear. So they are suppressed more than in general. So it's related to the fact that this chaos calculation is completely determined by the symmetries, independently of the detailed matter content and the detailed dynamics. And you can actually compute that in general the size of the stringy corrections in a general black hole. Non-extremal black hole, and you can see that as you take for a fixed ratio between LS. So I said before, I wrote a formula where the correction to the maximal exponent was something like LS over RADS, right? Something like this. This is some typical radius. Now, in fact, this is qualitatively correct, but when you approach near extremal black holes, actually, there is an extra suppression here, which you can write it as the near extremal entropy over the extremal entropy, which is going to 0 as you take extremality. So for a fixed ratio of these quantities, of the size of the string scale, you can see that the stringy correction goes down.
Thank you.
Yeah.
Okay, I have one comment, one simple point, that the exponent in the bulk is actually not classical, but it is it's related to the Hawking temperature, so it comes with an h bar. So in some sense, it's also quantum mechanical.
Well, yeah. So the h bar there comes in the translation between the two times, the boundary time and the.
Yes, that's right. The other comment is, I mean, it's a common question, but you had a slide on the fact that we don't understand the Virasoro algebra or the central charge in the SYK model. Now, suppose, because you have this reparameterization symmetry, there is an algebra. Suppose you assume that that algebra has a central charge. Suppose you assume that it's very large. If you do those assumptions, and then you can look at the coadjoint orbit of that algebra. And that coadjoint orbit turns out to be turned out to describe Polyakov's two-dimensional gravity in a certain gauge. So you get that type of two-dimensional gravity theory. You introduce boundary terms by the usual consistency of the variational principle. And one more thing you do is that you add a cosmological constant from outside, just like you add a Hamiltonian or something. Now, if you study this system, then you get the Schwarzian with all the parameter matchings which agree with the SYK model. So wouldn't you say that in some sense, in this perhaps roundabout way, that there exists a Virasoro algebra with a large central charge in the SYK model?
What is the central charge?
I don't know the number, but it's proportional to n.
Maybe. Maybe you understand it. I don't know. I haven't.
Okay.
Maybe something I ignore. So, but that I don't know. So, people have yeah. Yeah. Maybe I won't say anything.
So, Juan, you said that the SYK model per se doesn't have a very simple, at least, string theory realization, although there might be some complicated one. But to turn it around, as you've yourself emphasized, since we know now, since generically extremal rise to Nordstroms in, say, asymptotically ADS space give rise to this Schwarzian theory, at least at low energies, you might ask, what are the string theory microscopic models which give rise to the near ADS2 conformal dynamics? And there's obviously a class of these models, but which ones might be more tractable or interesting to explore?
Right. Well, yeah, there are many configurations in string theory that have ADS2 vacua. So, I mean, you can start from either ADS5 and consider a charged black hole, and that has an ADS2 geometry. And so there, and well, there are similar situations in ADS4, and also you can consider the quantum mechanics of brains. You can consider bound states of brains and consider the quantum mechanics of these brains, and that should also describe somehow the this nearly conformal theory. But in all these examples, it's hard to isolate the piece that gives you this the ADS2, and does not introduce extraneous elements. So one that is pretty popular is to think about, let's say you start from ADS3, CFT2, right? And then you consider configurations with momentum, and then you take the low energy limit. So that's that I guess has been the simplest way to, well, the traditional way. In string theory, we've been understanding ADS2, but it's not clear whether we need the whole two-dimensional field theory. And in fact, the SYK model, I think, shows that well, you can get it from a simple quantum mechanical model. You don't need two-dimensional field theory. You don't need another dimension. So I think it's interesting to, even in these two-dimensional field theories, that you say, well, I have some mods with momentum, it's always been hard to isolate the piece that was responsible for the ADS2. And I think it's not a coincidence that it's hard. It's just simply the fact that you cannot take completely the extremal limit. You cannot go all the way to the, so in other flows between a higher dimensional field theory and some, let's say, lower dimensional or some infrared fixed point, you can, well, take the limit and decouple the two and really focus on the low energy limit. And here, it's always in some intermediate regime. And it's that we need to understand more clearly. Yeah.
Space and maybe.
Yeah, surely. I mean, I think yeah, some of these quiver quantum mechanics theories. As far as I know, there is no quiver quantum mechanics theory that gives a black hole with the finite area. So those, I think, are more complicated. I don't know the latest. Well, I don't know some of the papers on this, so I might be wrong about this. But even if you had the quiver quantum mechanics theory, you might have more degrees of freedom that you actually want. But well, one thing that we would like is a model that is dual to local physics in the bulk. So the ADS, the SYK model seems to be somewhat non-local in the bulk. So, so if we had a model that is also similarly solvable and perhaps not as solvable, but the simplest model that has a local dual in the bulk, that would be wonderful. So, yeah.
Actually, just following up on that question, if you took a extreme or rotating black hole,
yeah.
and then the limit that it's not precisely ADS2, but
yes. So an extremal rotating black hole is in the extremal limit. It's a warped ADS2 compactification. So and presumably all of this also is true that it's described by the SYK titled worm theory and so on, but it has not been checked explicitly. But I mean, there are some indirect checks, like the fact that the entropy is linear in time, and well, it's some qualitative argument that these things should hold in general. But one would like to also show it explicitly.
Can you hear? So we were live streaming this lecture on YouTube, and there's some questions online. So I'm going to read out one question, which is by somebody called Brain World.
Okay.
Who says, is there a good way to compute the entanglement entropy of two coupled SYK systems in a thermofield state? And is a replica trick or a numerical exact diagonalization relevant for this? So I'm just reading out the question.
Yeah, so computing the entanglement entropy of two SYKs in the thermofield double is the same as computing the entropy of just one SYK in the thermal Euclidean ensemble. And I didn't describe it, but once you have this solution, I mentioned that there is some conformal solution with 1 over t minus t prime, etc. Right? Then you can insert that solution into the action and evaluate the action, and that gives you the free energy of the system that includes the entropy. In fact, so that when you do that, you get essentially some constant, and that constant is the entropy. So it's directly the evaluation of the action.
Can you elaborate a little more on why you think that the bulk dual to the full SYK theory is perhaps non-local?
Yeah, so, well, there's been this calculation of 3-point functions by Rosenhaus and Gross, and the structure that they find for these 3-point functions is such that, let's say, for example, for high spins, it goes over to essentially free field contractions. So that's the structure we get, for example, in the Vasiliev-like theory. So that's a non-local theory in the bulk.
So you don't say it's like a Vasiliev kind of dual, or?
Yeah, it should be in that spirit. I mean, but Vasiliev is different because in Vasiliev you have all these fields would have exactly integer dimensions. So it's perhaps the formation of. I don't know what the Vasiliev-like theory would be in this case.
I see. Thank you.
Yeah.
So one last question, and then we'll. Yeah, Gonzalo. Yeah.
The SYK model, and how does it scale with Q, etc.?
Yes. So the question is, what's the ground state degeneracy in the SYK model? Well, if you ask about the exact degeneracy, it's just one. There is one ground state. But here, for example, I was discussing the ground state entropy. So that's a notion where you first consider these low energy states, right? And first take the Larsen limit, and then you take the low temperature limit. So in that context, there is some entropy. But let me try to clarify a little more what this means. So we have, let's say, a density of states, right? So rho of E. So we had some density of states that roughly was like this. So ground state entropy means that this density of states, rho of E, behaves sort of near the endpoint as e to the s naught times some function of E, right? So the ground state entropy is just this overall factor in the density of states here. So it's not directly related to the fact that there is a delta function or any feature like this. So it's just the overall factor.
Okay, so I think we'll conclude here. There, of course, a lecture also tomorrow. Let's thank the speaker once again.